Static friction, part 1. All surfaces have this tendency to stick together, and this sticking interaction we call the force of static friction. This wood block sitting here on the tabletop at the moment, I know that there is no force of friction on the block as it sits here at rest. I know that because a force is a vector, and a vector has a direction. So if you think that there is a force of static friction on the block due to the tabletop at the moment, then you have to tell me what direction that force points. You're forced to make a choice. What's the direction of friction? And as soon as you made a choice, say friction points that way, then I'd say, well, according to Newton's second law, that force is going to cause acceleration. If there's a force of friction that way, then this block ought to start accelerating that way on its own. But of course, a block at rest doesn't do that. It just sits there. Friction doesn't show up unless it needs to. I can make friction show up by attaching this spring scale and trying to drag the block across the table. So if I don't pull, there's no force of friction here on the block due to the table. But as soon as I pull with a force of 1 Newton here, then there's static friction showing up to oppose me. The block, however, is not moving. It's still in equilibrium. I can increase my applied force to 2 newtons, 3 newtons, 4 newtons. And each time, static friction has increased to 2, 3, 4 newtons, matching my applied force. It's only as big as it needs to be, and exactly as big as it needs to be in order to prevent this force from causing slippage. But however, you know that if I pull hard enough, the block will slip. So that means that at some point, I can break static friction, as we say. Static friction grows to match me, but it can only grow so big. There's a maximum value of static friction. As soon as the block starts to move, starts to slide, then friction changes in character. For an object that's actually sliding, slipping, we say that the friction that's present now is kinetic friction, and we'll investigate that in another video. But for the moment, I want to look at that moment when we change from static friction to kinetic friction. That moment where we just break static friction, that moment where we start to slip. So look at my force that I'm applying here. I've got to pull hard enough to hit that maximum force of static friction. But then, when it starts to move, look at the kinetic friction that takes over. So I can pull to 2, 3, 4, 5, 6 newtons, and then breaking static friction, it dropped down to about 4 newtons. I needed to hit about 5 or 6 newtons to break static friction. That's as big as static friction could be, but then I only needed about 4 newtons to keep it moving. That's 4 newtons of kinetic friction, suggesting that kinetic friction is weaker than static friction. So watch here, and you'll see it again. It'll jump to a maximum value and then drop down to a lower value to keep it moving. So I can break static friction and then need a smaller value to keep it going. All right. That brings us to the most common misconception about friction, which is that friction tends to always slow things down. Not the case. This clipboard here can serve as kind of a tray. If I place this mass onto the tray there, without touching the mass, I can cause the mass to accelerate to the right and stop. I can make it accelerate to the left and stop. I can make it accelerate in any direction I want to without touching it. You know, forces cause acceleration. So what force is accelerating this mass here? Well, it's not my hands. My hands are not touching the mass. I don't have telekinesis. The only thing touching the mass is the tray. The surface of the tray in contact with the underside of the mass is exerting static friction on the mass. Another name for static friction is traction, that tendency for a surface to sort of push another surface along with it, tendency of the surfaces to move together. Now, if I pull the tray hard enough, if I give the tray a big enough acceleration, I can break the static friction between the mass and the tray. So if I give the tray a big acceleration to the right, the static friction between the mass and the tray was not strong enough to keep the mass in place. I can pull the tray to the right again, and I broke static friction between the mass and the tray. I can keep doing that, breaking static friction between the mass and the tray, all the way until the mass slips off, And what I've done is sort of slide the tray out from underneath the mass by giving the tray a bigger acceleration than static friction can provide to the mass, because static friction has a maximum value. Incidentally, that traction, that ability of static friction to speed things up, is exactly what helps you walk every time you take a step. Left foot, right foot, left foot, right foot. When you step and push off with your right foot, that's static friction between your foot and the floor, that traction pushing your body forward. And then static friction on your left foot pushing you forward. And then static friction again on your right foot pushing you forward. Static friction speeding you up, moving you along. So, friction doesn't just slow things down. It can also speed things up. Friction's primary mission here is to oppose slippage. So we must destroy that misconception that friction always slows things down. Not the case. What friction does, static friction does, always does not oppose motion. What it opposes is slippage. It tries to keep those surfaces stuck together. The static in static friction means the two surfaces are not moving relative to each other. They're stuck to each other. So either they're both not moving, both surfaces, or both surfaces are moving together, like the mass being carried on the tray. Surfaces are sticking together. That's what static friction is all about. We abbreviate it as a F with a lower subscript FS, as in friction of the static variety. FFS for static friction. If you ask, what direction is static friction pointing in a given situation? Well, whatever direction it needs to point to oppose slippage. How big will static friction be in any given situation? Well, as big as it needs to be to oppose slippage, up to some maximum value. Let's look at a couple of example cases. Suppose I've got some bowl of soup here that I'm going to push across a tabletop. And let's look at a few different scenarios as I push harder and harder. First, if I'm not pushing, then there is no force of friction. There's just the normal force and the force of gravity, which I've stopped labeling in the rest of the diagrams to keep things from getting too cluttered. If you're not pushing, there's no friction. As soon as you start pushing a little to the right, a little force of static friction shows up to oppose that, matching my applied force, keeping the bowl at rest, preventing the bowl from slipping. If I push harder, in fact, if I push as hard as possible before the bowl starts to slip, then my applied force will hit the maximum value of the force of static friction. It grows to a certain maximum value, and it's just about to slip if I push any harder. So if I do then push harder, we say we break static friction, the bowl starts to slip, and then friction changes from static friction to kinetic friction, FFK. And there we see this kinetic friction force is weaker than that maximum static friction force, as we saw on the spring scale. So this sequence of events can be summarized by this graph here, the graph of the applied force of, the force of static friction versus the applied force. And they are, there's a linear function with a slope of 1. The static friction force equals the magnitude of the applied force. It matches the applied force. It's only as big as it needs to be up until some maximum value, beyond which we say we break static friction and kinetic friction takes over. So that's static friction trying to prevent the block from moving, but of course static friction makes things move all the time. I said block, I meant bowl of soup, because here's now our bowl of soup on a tray being carried across the room, moving to the right. So the bowl is in contact with the tray, moving to the right, and let's say at first it's being carried in such a way that it's moving with a constant speed. The tray and bowl are not accelerating. In that case, there is no force of friction between the bowl and the tray, moving at a constant speed, so we're in dynamic equilibrium here. Normal force balancing the force of gravity. That's it. Now let's say the person carrying the tray pushes a little harder to accelerate the tray to the right a little bit. To keep the bowl moving with the tray, to keep the tray from sliding out from underneath the bowl, the tray will now need to exert a force of static friction on the bowl to the right. That unopposed force of static friction on the bowl will accelerate the bowl to the right, so the bowl's acceleration matches the tray's acceleration, and they continue to move together without the tray sliding out from underneath the bowl. We can accelerate the tray with a greater acceleration. In fact, there will be some maximum acceleration that we can give the tray, at which the static friction on the bowl from the tray is at its maximum value, giving the bowl its max acceleration. If we give the tray acceleration any bigger than this, static friction can't grow any bigger than this to increase the bowl's acceleration. So push the tray with any greater acceleration, and then the tray will start to slip out from underneath the bowl. We'll have broken static friction. Static friction can't get any bigger, so the tray starts to slip out. The bowl will look like it's sliding towards the back of the tray. Actually, it's the tray sliding forward because the bowl's acceleration is not as big as the tray's acceleration. And as soon as the bowl starts to slide, then the friction changes from static to kinetic. There's FFK taking over. Once again, that force of kinetic friction weaker than the maximum force of static friction. And we can summarize that with this graph similar to the last one. We're plotting the acceleration of the bowl, which comes from Newton's second law. It's only this force of static friction accelerating the bowl forward divided by the mass of the bowl. So the acceleration of the bowl versus the acceleration of the tray. And the two are equal. Here's a line with a slope of 1 up until some maximum acceleration that the bowl can reach. Here is where the force of static friction trying to keep the bowl matched to the tray, it can no longer get any bigger. And at that point, if the tray has any greater acceleration, the bowl can't keep up and will start to slip.